Bismillahirrahmanirrahim. Actually, the chapter is subsurface flow considerations for the design of barrage, and what we are discussing right now, the theory is basically to consider the subsurface flow under the barrage, and we know that when water flows under any hydraulic structure in the porous medium, then it causes two problems. One is the uplift pressure, and second is the undermining or piping. So these theories, all these three theories, maybe Bligh's theory, Lane's theory, and the Khosla theory, they give us the how to compute the uplift pressures accurately, and what is the solution to control the undermining or piping. That basically we have discussed. And according to the Bligh's theory, you know how we can compute the uplift pressure at any point? Someone should respond me. Yes. How we can compute uplift pressure at any point? Maybe here, 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 and anywhere. According to Bligh's theory, compute the head loss up to that point. Okay. And how to compute the head loss up to that point?
सर पहले क्रीप लेंथ निकालते हैं उस पॉइंट तक.
जी उस वही पॉइंट तक क्रीप लेंथ निकालें डिवाइडेड बाय द टोटल क्रीप लेंथ. इसका जो रेशियो ऑफ द क्रीप लेंथ है, it should be multiplied by the total head, capital H, available on the upstream side. So this will give you the head loss. And then how to compute the uplift pressure head or the uplift? Total head में से head loss को minus कर दें. So you will get the basically uplift pressure at any point. And what happens to the uplift pressure as we move to the downstream? क्या होता है? बढ़ता है, कम होता है?
इंक्रीज करता है.
डिक्रीज करता है, कम होता है, क्योंकि हेड लॉस बढ़ता जा रहा होता है. ओके. एंड नाउ according to Bligh's theory, how we can make a structure safe against piping or undermining?
तो sheet piles provide करते हैं.
No. What is the criteria? Criteria is this one. The hydraulic gradient should be less than hydraulic gradient prescribed by the safe hydraulic gradient prescribed by the Bligh's. Okay.
Excuse me, sir.
So this H over L should be less than 1 over C. जी भाई.
सर जो लॉबी में वेट कर रहे हैं उन्हें लेट इन कर लें.
अच्छा जी. कुछ ऑलरेडी शामिल नहीं है. ओके. ठीक हो गया, समझ आ गई भी बात?
Yes,
actually this is the criteria given by the Bligh. Now come to the Lane. What the Lane says? Lane only tells that contribution in computing the creep length by the horizontal surfaces is not that much as taken by the Bligh. Lane says the contribution by horizontal surfaces is very less. How much less? 1/3. So 1/3 of H plus V, all the vertical surfaces creep length, that is equal to the total creep length. So it means by the Lane theory. So if we are using Lane theory, so how we can compute the uplift pressure head or uplift pressure? According to Lane theory, the equation will remain same. We have to compute head loss at that point. And how we have to compute head loss? The creep length up to that point divided by the total creep length into the capital H. So only difference in the Lane theory, how to compute the creep length. So we have not to consider much to the horizontal lengths. Horizontal lengths would be divided by 3, and then verticals would be added. So if you have computed head loss up to any point, then how we can compute the uplift or residual pressure head up to that point? The capital H, that is simply equal to capital H minus head loss. Now, how to check a hydraulic structure for mining, undermining, or piping? That is it safe or not safe? The criteria is very similar as given by the Bligh, that the hydraulic gradient in the actual structure should be less than safe hydraulic gradient prescribed by the lane. So these subscripts L, they represent the lane. So lane has given different values for the for his coefficient CL. All right. And also lane has given a different creep length concept. So according to him, the horizontal creep length does not matter much. Horizontal floor length. So according to creep, according to lane theory, if any hydraulic structure is failing in the undermining or piping, what is a better solution? क्या करें?
Sir, we can provide more vertical cutoffs, more vertical sections, so that
yes. So we have to increase this total creep length.
Yes, sir.
And how we can increase this total creep length? Not by increasing the horizontal surfaces, by increasing the vertical lengths of the sheet piles. Maybe introduce more sheet pile or go length of the sheet pile should be deeper. So this is the main difference between the Bligh's theory and the lane theory concepts of the creep theory. Now the third theory is the Khosla theory or the Khosla method of independent variables. So it is based on potential theory of the classical hydrodynamics. And according to this theory, actually this theory is based on the Darcy's law. And then the basic concept given by this he does not say that as the water creeps under the hydraulic structures as explained by the Bligh and Lane. He differs them. He says that the underground water does not move like that. How he says that it moves? It moves in the form of streamlines. And he has given the same concept that the water flows under the hydraulic structure as a flow net is formed under it. Okay, and you know that the flow net has the psi lines and phi lines. So psi lines are the flow lines, are the stream lines, and the phi lines are the equipotential lines, which we have seen in the very beginning. We have seen many flow nets, and those lines represent the equal pressure heads. So actually, that flow net governing equations for phi and psi are these. So d square phi over dx square plus d square phi over dy square, that is equal to 0. And this is a Laplace equation for phi. Okay. And phi, you know very well, is a function of x and y. So it depends on x and y and is known as velocity potential function. Similarly, if there exists a velocity potential function, it means then there must exist a stream function psi, which must satisfy this equation. So partial d squared psi over dx squared plus d squared psi over dy squared, that is equal to 0. And this is the, again, one more Laplace equation. But this is the Laplace equation for psi. So whereas phi for different values f, x and y gives equipotential or equipressure lines. As you know, we have seen in the previous lecture when we saw several flow nets. And psi gives a set of streamlines which are at perpendicular direction to the phi lines. The pattern thus obtained is known as a flow net. So actually, Khosla says that the subsurface flow which takes place under the hydraulic structure does not follow the creep theories, but it moves as flow nets. Now, what are the main principles of this theory which are given here? Let us discuss one by one. The first is that the seepage water does not creep along the bottom contour of impervious floor as stated by Bligh and Lane. But on the other hand, this water moves along a set of streamlines. That is, he has given the concept of the flow net. So that is the first difference between the previous two theories and the Khosla theory. So what do you think? Who is more right? Whose approach is more logical? Do you think does water flows, it creeps under the floor, touching the bottom of the concrete floors?
Khosla
No, sir.
No, so the first Khosla is more close to the reality.
Yes, sir.
Number two, the seepage water, while flowing through the porous medium, it exerts a force. At each point, in which direction it exerts a force? In the direction of flow. Okay. And what would be that direction? That would be tangential to the streamline. So if this is the streamline, so at any point, if you draw a tangent, so that is the direction of seepage force. So seepage force. So when the water seeps in the porous medium, it applies a force in the direction of motion. And so if you want to know the inverse direction at any point, then on a streamline, just draw a tangent. Okay. So a seepage force is being exerted by the water when it flows. Number three, and this is very logical. Number three, the force has the maximum disturbing tendency. Whose force? Which force? Seepage force. It has maximum disturbing tendency where? At the exit end. By the way, what do we provide? At the exit end of the downstream concrete flow. What we provide?
Sir, we provide the sheet pile.
downstream.
We provide a downstream sheet pile. Okay. Because the direction of this force at the exit point is vertically upward. Suppose if we do not provide that downstream sheet pile, then this flow will take place like this. Now this is the gate, this is the capital H. So these lines are streamlines. ये streamline है ना, ये यहाँ से निकल रही है, बाहर पानी आ रहा है. And what about these lines? These lines are the equipotential lines. ये pressure बता रही हैं. What is happening to the pressure head as we move downstream? यहाँ pressure ज़्यादा होगा. ये आगे जैसे हम जा रहे हैं तो यहाँ pressure head कम हो जाएगा. Okay. So this is equipotential line. It gives that the pressure it had along these all points of this line, pressure heads are same. So you see that these are the 3 piezometers which are being installed, and at this point, and how much is the pressure head? कितना है? Same है ना H? Okay. So pressure head is same. So because this is an equipotential line, it gives the points of, or it joins the points of equal pressure or equal pressure head. So we will go back, and what he is saying, Khosla says that where the seepage force have maximum disturbing effect, at what location?
Downstream end, sir.
Downstream end, like here. Now these seepage, these streamlines are emerging at this point. So at this point, the disturbing effect would be maximum. So now, because he said that at this point, this exit gradient would be vertically upward, which is shown in this diagram. Now this is a concrete structure, and this is the head of water. So let's say if these are the streamlines, these all are streamlines, and he has not shown equipotential lines here, just he has shown these streamlines. And then what he want to explain that at any point on the streamline, if you draw a tangent, that would be the direction of seepage force, which the underground water applies here. Okay, and what is this one? If we consider a soil particle, then this would be the submerged weight, which is in the downward direction. But now see, at another point, this would be the direction of the seepage force. If we consider here, this is the tangent, and this would be the direction of seepage force. But at the exit, what would be the direction of seepage force? Exactly vertically
Upward.
upward. Yes. And what would be the direction of submerged weight? It is always downward. It is always, huh? Doesn't matter that it is at the exit point or anywhere else. So we know that the submerged weight, it always acts in the downward direction. So now we will go back here. So now the point number 4. Which he said that the for soil grain to remain stable, where to remain stable? At this point. Okay. If the soil particle is remaining stable at these points and only water is going out, then what we will say that undermining or piping is not taking place. But if the fine particles from here are removing, they are also moving outside due to the seepage force. Then, of course, there would be undermining. So now what he is explaining that how this soil particle will not move or will move. It depends on what? He says that number 4, for the soil grain to remain stable, when it will remain stable, the submerged weight of the soil grain should be more than the upward seepage force, which is the disturbing force. Right? So according to him, if this submerged weight, why submerged? Because the soil particle is in water. So now the resultant weight would be the submerged weight, because the weight will act in downward direction and buoyant force in the upward direction. So the resultant is submerged weight. And this submerged weight, if it is greater than the produced seepage force by the seeping water, then this soil particle here would be stable. Could you get it? Now, number 5, the disturbing force. What is disturbing force?
Seepage force.
Seepage force. Seepage force is disturbing force. Okay. The disturbing force at any point is proportional to the gradient of pressure of water at that point. So that is dPL over dL. This is the gradient of the seepage force. Where is that diagram? here. Now here this would be the direction of the seepage force. Here this is the direction of seepage force, and then you can compute the accordingly change in pressure with respect to change in length. So that is the gradient of pressure. And as this increases, so seepage force increases. Number 6. This gradient of pressure of water at exit end is called the exit gradient. So the value of the dP over dL at this point, at these points, that is called as exit gradient. This is the number 7. The head loss does not take place uniformly in the direction proportional to the creep length. Actually, according to Bligh and Lane, the head loss was proportional to the creep length. Here it is not like that. Number 8. The safety against piping and undermining cannot be obtained by providing sufficient floor length. By increasing the floor length, we cannot obtain safety against piping. But can be obtained by keeping the exit gradient well below the safe limit. What is the safe limit? That is the critical value given by the Khosla. So number 9, the piping and undermining starts from downstream end. This we know very well. The piping will start from downstream end of downstream concrete floor if the exit gradient is unsafe. Unsafe means if the exit gradient is more than the safe gradient, okay? And if piping is not checked, what do you mean by checked? If the piping is not stopped, piping travels towards the upstream side. Could you follow it? So if the piping here is not stopped, how we can stop it? By proper designing of the barrage, considering surface flow considerations. If the piping is taking here, then that piping will go down and it will go upstream. So once here there would be piping, then here the void ratio will increase a lot, and this structure may subside or may settle down, and then it may break and there will be damage to the downstream part of the structure, and then maybe the whole. Then it is very easy that the structure may be washed away. So if piping not checked, it means not stopped, piping travels upstream towards the upstream side. Therefore, it is absolutely necessary to provide how we can, control this one. We have to provide sufficiently deep sheet pile at the downstream end of the downstream concrete flow. So according to Khosla, the downstream sheet pile is very important, and its length of the downstream sheet pile is very important to reduce the value of exit gradient. Could you follow it? क्यों भाई ठीक है? Yes. So these are the 9 main points which we keep in mind, which has been given by the Khosla.
Yes, sir.
जी भाई.
Sir, dP over dL वाला concept समझ नहीं आया.
Change in pressure with respect to length. So this is the gradient of the pressure. You know that uplift pressure, you have computed uplift pressure at several points. And what happens to the uplift pressure as we move towards the downstream? It reduces. है ना, कम हो रहा है ना?
Yes, sir.
तो उसका कितना कम हो रहा है? 1 फुट लेंथ में या 1 मीटर लेंथ में जो कमी आ रही है in the pressure, that is dPL over dL. So that is the change in pressure with respect to unit length. ठीक है भाई?
ओके सर, ये वेरी करेगा along the length या कांस्टेंट रहेगा?
No, actually in case of your Bligh's theory and the other theory, Lane theory, वो क्या कह रहा था? Bligh's theory वो तो कांस्टेंट बता रहे हैं ना, चेंज हो रही है, लेकिन इसमें कांस्टेंट नहीं है, दिस इज चेंजिंग.
ओके सर.
ओके, अब खोसला आते हैं सोल्यूशन की तरफ. भाई सोल्यूशन हमें खोसला से क्या चाहिए, किस चीज का सोल्यूशन चाहिए? which solution do we need for the barrage? हमने दो चीजें निकालनी है यार. एक तो अपलिफ्ट प्रेशर कितना होगा at several points of the barrage structure, ताकि हम अकॉर्डिंगली कंक्रीट फ्लोर की थिकनेस डिजाइन कर सकें, and it should be safe. So it means we need the values of the uplift pressures, our pressure heads. And what else do we need? We want to avoid undermining our piping. तो उन दोनों के लिए अब हम खोसला ने एक सोल्यूशन दिया है ना. तो खोसला ने फिर क्या किया है कि ये जो टू अपलिफ्ट प्रेशर जो कंप्यूट करना है एट की पॉइंट्स ऑन of a sheet pile and at corners of depressed floor, वो कैसे करना है? So he has given that one in 3 cases. उसने 3 केस बना दिए. The case number 1, 2 and 3. Let's see what is the case number 1. He says that a straight horizontal floor है of negligible thickness है. Concrete floor की thickness कितनी है? Negligible. Means 0 or close to 0 with a sheet pile line on the upstream and downstream. ये केस नंबर 1 है. अगर एक concrete floor of negligible thickness and there is a sheet pile on upstream side or down, this is the case number 1. Now this is the concrete floor and there is a sheet pile on upstream side, E1, D1, C1, and this is the concrete floor of negligible thickness. Please mute your mic. And this is the downstream sheet pile, EDC. This is how we define a sheet pile. Okay. तो पहला जो केस है वो उसने दिया है कि अगर हमारे पास कंक्रीट फ्लोर है of negligible thickness और sheet pile provide किया है either on upstream side or on downstream side, तो फिर हम uplift pressures कैसे निकालेंगे? ओके. नंबर 2, a straight horizontal floor depressed below the bed. depressed below the bed का क्या मतलब है? thickness बहुत ज्यादा है फ्लोर की, enough thickness है फ्लोर की, but without any vertical cut-offs. उसमें वो नहीं है sheet pile. ओके, that is the second case. तो ये किस लिए है सेकंड केस? ताकि जो थिकनेस का इफेक्ट है वो लिया जा सके. नंबर 3, a straight horizontal floor of negligible thickness with a sheet pile line at some intermediate points. जो केस 1 था उसमें तो शीट पाइल था या अपस्ट्रीम पे या डाउनस्ट्रीम. अब बीच में भी शीट पाइल हो सकता है ना, विच इज कॉल्ड एज इंटरमीडिएट शीट पाइल. तो वो केस 3 में खोसला ने डिस्कस किया है कि there is a floor and there is a sheet pile. So now this is the case 2 example. And case 2 में क्या है भाई? thickness of floor बहुत ज़्यादा है, sufficient है, तो we need to determine the values of the D1 dash and D dash. पहले हमने क्या निकाला? So due to, and how, what is small d? Small d here is the thickness of the floor and small b is the length of the floor. What is the case 3? case 3 में हमने कहा है कि कोई intermediate sheet pile है, alright, और फिर pressures EDC points पे कितने होंगे? That is the concept given by how to compute the uplift pressures by the Khosla. Now we would like to discuss one by one. So this is the case number 1. case number 1 में क्या है? ये concrete floor है of negligible thickness. This is some head is here of depth of water, and a sheet pile is provided on upstream side या on the downstream side. How much is the length of the sheet pile? कितनी है भाई?
small d.
Small d. And how much is the length of the concrete floor? वो कितना है? Small
b.
Small b. Now we are interested to know the uplift pressure at point E1, at point D, at point C1. C1 is this point. Now where my cursor is I have placed. So now phi C1, यहाँ पे कितना pressure है? 100 minus phi E, where phi E is here, okay? So that is the uplift pressure here. So 100 minus phi E means what would be the units of the answer? क्या होना चाहिए? Percentage में? So in this way you can get phi C1. And what is the phi D1? अच्छा, phi C1 किसके बराबर है? Uplift pressure 100 minus phi E, और phi E इधर pressure head है. अच्छा, what is the phi D1 equal to? यहाँ पे कितना pressure होगा? So that would be 100 minus phi D, and D is the uplift pressure at point D here. Okay, now come to this side. So how we can compute the uplift pressure at point E? So phi E, here the pressure is 1 over pi cos inverse lambda minus 2 over lambda. And what is the lambda? Lambda is 1 plus under root 1 plus alpha square over 2. And what is alpha? Alpha is the ratio between B over D, where B is the length of the concrete floor and small d is the length of the sheet pile, yeah, depth of the sheet pile. Okay. So this is the case one. It gives us the uplift pressures on the points of either of upstream sheet pile and or of downstream sheet pile. Now how many are the points? कितने पॉइंट है? और फाई डी कैसे आएगा? फाई डी ये आ जाएगा, है ना, लैम्डा माइनस 1 ओवर लैम्डा. सो यहाँ पे कितने पॉइंट हैं? E1, D1, C1 3 पॉइंट ये हैं, E, D और C 3 पॉइंट ये हैं. एंड हाउ मेनी यू हैव द इक्वेशंस? कितनी? 4. व्हाई नॉट 6? भाई 6 पॉइंट है. वी नीड द pressure heads at these 6 points. So why these two equations are not given?
Sir, 2 repeat हुए हैं points ना?
कैसे repeat हुए हैं यार, बताओ.
सर कुछ पॉइंट जीरो होगा pressure
है?
सर E1, C1 और E और C.
नहीं, repeat तो नहीं हुए यार.
उनका सेम लेवल है.
उनका प्रेशर सेम होगा.
उनका लेवल सेम
होंगे एक पॉइंट पे.
कहाँ पर प्रेशर सेम होगा? Where the pressures would be same?
सर E1 और C1 पॉइंट पे.
E1 और C1 पॉइंट पे प्रेशर सेम होगा, ये आप कह रहे हैं ना, और आप ये भी फरमा रहे हैं कि पॉइंट E और C पे भी प्रेशर सेम होगा. यही कह रहे हैं?
Yes, sir.
If you are saying this, then what is the role of this vertical sheet pile? ये तो कुछ भी नहीं कर रहा. जो प्रेशर हेड इधर है वही उधर है, तो यार इसका फायदा क्या है? You are providing so deep sheet pile and you are saying that it is doing nothing. ऐसा नहीं है भाई. यहाँ पर प्रेशर हेड ज्यादा है जैसे हम मूव करेंगे तो प्रेशर हेड को क्या होगा, कम होगा, है ना, बिकॉज ऑफ द हेड लॉस। तो E1 पे प्रेशर हेड ज्यादा है, C1 पे प्रेशर हेड कम है, या अपलिफ्ट प्रेशर कह लें वो कम है ना। तो अब बताएं व्हाई द खोसला हैज गिवन 4 इक्वेशंस फॉर 4 पॉइंट्स। तो दो उसने इक्वेशन दी नहीं, खोसला भूल गया था, क्या हुआ? अच्छा चले, मैं अब ये सवाल आपसे ना किसी और तरह पूछता हूँ। व्हाट अबाउट E1, हाउ मच शुड बी द प्रेशर हेड, अपलिफ्ट प्रेशर E1 पे कितना होना चाहिए?
So maybe
Sir,
we can
HK
find
equal.
the pressure at E1 by difference of C1 and phi C1 and phi D1.
नहीं यार, मैं प्लीज लिसन माय क्वेश्चन। हाउ मच शुड बी द प्रेशर हेड एट पॉइंट E1?
Sir, 100.
if it is capital H,
Sir, HK equal होगा कैपिटल H.
कैपिटल H के बराबर होगा, दिस इज 100% होगा ऑफ H, ऐसा ही है। तो खोसला को क्या जरूरत है इक्वेशन दे? अच्छा, नाउ कम टू दिस पॉइंट C, हाउ मच शुड बी द प्रेशर हेड एट C, और द अपलिफ्ट प्रेशर एट C कितना होगा, होना कितना चाहिए? इफ द डेप्थ ऑफ वाटर एट पॉइंट C इज 0, ये देखें यहाँ डेप्थ ऑफ वाटर है, यहाँ नहीं है,
Zero, sir.
so it should be 0. So that's why Khosla has not given these two equations to compute the pressure, uplift pressure at E, यानी phi E1 की इक्वेशन भी नहीं दी, phi C की इक्वेशन भी नहीं दी, because these uplift pressure we already know. Is it clear? आगे चलें?
Yes, sir.
Now the case number 2. Now B is the length of the concrete floor, where the d, small d, is the depth of the concrete floor, and it is sufficient depth or thickness. So there are 2 points, d1 dash and d dash, and how you can compute this pressure, uplift pressure. So phi d dash is 2/3 of phi E minus phi d, which we already know from here, and plus 3 over alpha square. And this one, phi d1 is equal to phi d1 dash, that is 100 minus phi d dash. So this is the relationship between these pressures at point d1 dash and d dash. Now what is the case 3? There is an intermediate sheet pile, and now these points are E, D and C. Now B was the total length of the concrete floor. अब इसने क्या किया है, B1 is the length of concrete floor upstream of the intermediate sheet pile, and B2 is the length of the concrete floor on downstream of the intermediate sheet pile. Now how to compute pressure at E, D and C? So he has given these 3 equations, phi E, phi D, phi C, and it's a function of, किसका function है भाई, ये जो तीनों प्रेशर है, दो चीजों के फंक्शन है, lambda and lambda 1. So you can see here lambda 1 and lambda 1 and lambda 1 in all 3. Now what is lambda and what is lambda 1? It is defined. So lambda is 1 plus alpha 1 square under root plus 1 plus alpha 2 square under root over 2. And what is the lambda 1? That is 1 plus alpha 1 square, ये प्लस की बजाय माइनस साइन के साथ है. And what is the alpha 1 and what is the alpha 2? So alpha 1 is B1 over D, so B is this and D is the depth of the sheet pile, and alpha 2 is equal to B2 over D, and B2 is this floor length after the sheet pile or downstream of the sheet pile. So these are the three cases which were given by the Khosla to have the uplift pressures. Now for simplicity, Khosla has plotted curves for all these three cases. As you just by seeing these curves, you can very quickly compute the uplift pressures. For example, this is the case 1. So now for point D1 and C1 are E and D. So he has directly given the phi E. So this is the uplift pressure at point E. This is the uplift pressure at point D dash. Yeah, D. Sorry, D. And this is the uplift pressure at phi D dash. Okay. So this is the depressed floor. D dash means depressed floor, which is the case number 2 here. This one is the D dash. Okay. So what you have to compute? So you have to compute the values of 1 over alpha, which is D over B, where B is the length of the concrete floor and D is the depth of the sheet pile. So compute this ratio, and once you know this ratio and you touch this graph, so that should be the value of the uplift pressure phi for that purpose. Similarly, if you are interested to determine the uplift pressure at point D, which is this one, so just compute this alpha value, and where it touches this, so you can get in percentage that how much percentage is the uplift pressure we have. So where H is the total end, and similarly at point E, you can get this is the point E inside, and for any value of D over alpha, you just touch it and you can get the uplift pressure. So similarly for here, this is for the case number 3 for the intermediate sheet piles, and just compute the ratio B1 over B, and you know what is B1? B1 is the length of the concrete floor on upstream of the intermediate sheet pile, and B is the length of the total concrete floor. Just compute this and for any value of the alpha you need to compute, okay? And for any value of the alpha and this, where it intersect, you just go left and you can find the percentage of the capital H, that is the uplift pressure, which is occurring here on this point E, D, or C, okay? So this is how you can find the uplift pressure by using the Khosla's curves. ये figure किस चीज की है भाई? These are the Khosla's curves. तो उसके तीनों cases इसमें आ गए, and these are very comprehensive curve. And instead of using these equations, you just we keep these curves while designing a barrage for the subsurface flow, and we just consult this curve and find the uplift pressures at various points. क्यों भाई ठीक है भाई?
Yes, sir.
Okay, now shall we move next? Now, what is the
B1
solution given by? Sorry?
B1 over B में सर ये B1 क्या है?
B1, I explained you, this is the B1, that is the length of the concrete floor upstream of intermediate sheet pile. ये वाली length concrete floor की B1 है, ये वाली length B2 है, total length B है, तो यहाँ से लेकर यहाँ तक, okay? Now, what is the solution given for the undermining or for piping by the Khosla? तो Khosla कहता है भाई exit gradient compute करो at downstream end. तो exit gradient जो डाउनस्ट्रीम एंड पे है दैट इज h over d into 1 over pi under root of lambda, where lambda is a function of the alpha and alpha is b over d, where d is the डाउनस्ट्रीम शीट पाइल की डेप्थ है और जो b है वो टोटल लेंथ ऑफ द इम्परवियस फ्लोर है या कंक्रीट फ्लोर है. ओके, सो h क्या है? मैक्सिमम सीपेज हेड. तो यहाँ से ये एग्जिट ग्रेडियंट निकल जाएगा बाय द खोसला. नाउ अब वो एग्जिट ग्रेडियंट तो निकाल लिया, लेकिन पता कैसे चले कि ये सेफ है कि नहीं? तो उसने सेफ एग्जिट ग्रेडियंट दिए हैं खोसला ने फॉर डिफरेंट मटेरियल्स लाइक शिंगल, कोर्स एंड फाइन सैंड. सो सेफ एग्जिट ग्रेडियंट है 1/4 to 1/5, यानी 0.25 से 0.2 तक है. कोर्स सैंड है तो 0.2 से 0.17 है, और अगर फाइन सैंड है तो 0.17 से 0.14 है. So we have to check the material under the barrage वो कौन सा है, and accordingly what do you think, shingle is a coarser material or fine sand is coarser material? कौन सा coarser material है?
सर शिंगल कोर्स मटेरियल.
कोर्स मटेरियल है, तो उसके लिए जो सेफ एग्जिट ग्रेडियंट की वैल्यू ज्यादा है या फाइन सैंड के लिए ज्यादा है? So as the material diameter becomes larger, so जो सेफ एग्जिट ग्रेडियंट है उसकी वैल्यू भी बढ़ जा रही है, क्योंकि उसका अपना जो सबमर्ज वेट है दैट इज गोइंग टू इंक्रीज. ओके, so now the 5 minutes are only left, and only the thing which is left is we have to apply corrections on Khosla's uplift pressures. अभी उस पर करेक्शन लगनी है. ये 3 करेक्शंस लगेंगी. करेक्शन फॉर म्यूचुअल इंटरफेरेंस ऑफ पाइल्स, नंबर 2 करेक्शन फॉर द थिकनेस ऑफ फ्लोर, ये जो थिकनेस ऑफ फ्लोर है, एंड द करेक्शन फॉर द स्लोप ऑफ द फ्लोर. आपको पता है अप स्ट्रीम ग्लेसेस हैं, डाउन स्ट्रीम ग्लेसेस हैं, तो स्लोपिंग फ्लोर भी हैं, तो उनके लिए भी करेक्शन लगेगी. एंड दैट करेक्शन वी वुड लाइक टू डिस्कस नेक्स्ट टाइम, बिकॉज Abhi only I think 5 minutes are left. So if you have any questions till now. Alhamdulillah. Okay. So these are the concepts given by the Khosla. So Khosla theory is more logical as compared to previous two theories. That is the Bligh's theory and the Lane theory, and that's why both these theories they are not being used nowadays. Nowadays we directly use the Khosla theory, or by flow net analysis directly we compute the uplift pressures and undermining etc. And with that I would like to stop today's lecture. If you have any questions, you are welcome.
Excuse me, sir.
Anji, yes.
Sir, can you further elaborate the exit gradient?
Exit. What is gradient?
So it's a slope actually.
It is slope. Yes. So it is the change in pressure with respect to change in length. So let us come here. So just consider this point and this point. All right. So there would be some pressure here, and here should be pressure 0, because if there is no water here. Or take, so how much is the change in pressure? That you know. And how much is the length? This you know. So This change in pressure over this length would be the exit gradient. उसका ये जो slope आएगा, that would call as exit gradient. Change in pressure with respect to change in length. All right.
Yes, sir. It's clear. Thanks.
So someone else, if he has some questions, then he or she is welcome. Ji. Okay, if you do not have any questions, then I would like to stop the meeting and also the recording.